All right, friends, this is it. The end of Unit 3. Ooh, we'll do that in a minute. The end of Unit 3 on today's show, tangent lines to approximate a curve in a small interval. And the idea here, if I can bring up a graph of just about anything. So you take some graph, you take x squared, and you say, wait a second. I want to zoom in on this curvy part of the graph. And you say, no, I want to zoom in on this curvy part of the graph. And the more you zoom in on a curvy part of the graph, the more it starts looking not like a curve at all. It looks like a line. What line does it look like? It looks like the tangent line. And so what we do in this lesson is we use the equation of a tangent line to approximate a curve in a small interval. That's the idea. Oh, if you want to sound smart at math parties, this whole property over here, this is called the idea of local linearity. The idea that if you stare really close at something that's curvy, it's not really curvy, it's straight. So by definition, if f is differentiable at x equals a, then L of x, which is f of a plus f prime of a times x minus a, defines the linearization of f at x equals a. And all we mean by linearization is that we're using the equation of the tangent line. I mean, you know that's the equation of the tangent line. It's got the same slope that the tangent line does. It passes through the point A, f of a. So this L of x function is nothing more than the linearization. It's the equation of the tangent line at x equals a. So how does that work practically? I want to use linearizations to approximate the square root of 65 and the cube root of 65. Now this is cutting edge 1783 because now we have calculators that approximate these things. But back in the day, if you were trying to approximate y equals square root of x at some number like 65, you were like, I don't even know. So what they did back in the day was they said, look, I'll make this linearization. And the linearization will be f of 64, because I know what a square root of function is at 64, plus f prime of 64 times x minus 64, and I'm going to let that line do a good enough job that we feel, okay, we're right about in the right spot. Plus or minus very small decimal places, we're going to be in the right ballpark. So L of x is going to be f of 64 plus f prime of 64 times x minus 64. F prime of 64. F prime of 64. F prime of 64. F prime of 64. Yeah, that does it. That does it. And just so we're clear, this L of x is just the equation of the tangent line. That's all it is. So if I want L of 65, which is approximately the square root of 65, because the tangent line isn't that much different than the curve in a small interval, you're looking at 8 plus 1/16 times 1. And it actually does a surprisingly good job of approximating the value we're interested in. Well, how about the cube root function? if I'm looking to approximate the cube root function, I go, I don't know what that looks like. It's curvy, it's weird, what do I do with that? So I come up with a linearization for the function. And I say, I want f of 64 plus f prime of 64 times x minus 64, because I know what that function is at x equals 64. That function at x equals 64 is 4. So f prime of 64, f prime of 64, f prime of 64, f prime of 64, f prime of 64. Yeah. So then L of 65, which is approximately the cube root of 65, that's approximately 4 plus 1 over 48. And that does a surprisingly good job. A quickie. I want to approximate ln of x plus 1 around the point where a equals 0. That's just a specific x value. And I want to use it to approximate the ln of 1.5. Huh. If I want to linearize ln of x plus 1, I need f at my special place plus f prime at my special place times x minus special place. Well, I can do that. F of 0, that's ln of 1. That's pretty good. Plus f prime of 0, I'll just stall for time on that one, times x minus 0. What the heck is f prime of 0? What is that? Oh yeah, that. So f prime of 0, that's that. And so that's just the line y equals x. And so if I'm interested in finding L of 1.5, yes. If I'm interested in finding the natural, no. If I'm interested in finding the natural log of 1.5, I have to find L of 0.5, because I want x plus 1 to equal 1.5. So x is 0.5. That's a half, which is approximately the ln of x plus of 1.5. As a side note, the ln of 1.5 is approximately 0.5 with a difference, with an actual difference of 0.095, which is not bad. I mean, it's not great, but it's not bad. Coach, why? Why are we, what are we doing? Coach, I mean, I love you a lot, and you've really been like fantastic forever, but why? That's a tangent line. And that tangent line has a slope. And that slope, Leibniz's notation is dy dx. Why does Leibniz use that notation? He doesn't use it anymore because he's dead, but he used that notation because he wanted you thinking about slope. He wanted you thinking that there was some actual change in y that this line was approximating, and some actual change in x that this line was approximating. So if I'm interested in this point over here, there is an actual slope of an actual secant. And that actual slope of that actual secant has a delta y and a delta x. And the idea behind the calculus is that in small intervals, this dy and that delta y are roughly the same thing. That's the idea here. So yes, you'll probably, because you're very good test takers, end up taking away from this lesson, so we just find the tangent line and plug it in. And the answer is sure, and that's going to earn you a point on a test, and you should be very, very proud of yourselves. But what we want to start thinking about going forward, long term, is that the tangent line in small intervals around a point of interest does a decent job of approximating delta y with dy, which is very useful in situations where dy is easier to find than delta y. There, I've gone on long enough. You stopped listening 5 minutes ago. We'll see you tomorrow.